Actually, this problem sort of segues into the next section, so let me go ahead and talk a little bit about this. Here we want to find the volume of the solid generated by revolving the region between the parabola x equal y squared plus 1, the line x equal 3, about the line x equal 3. Okay, so this red line right here is the line x equal 3, and you can see I've labeled it right there. And then x equal y squared plus 1 would actually be this region right here, and actually it would have it's a parabola that opens to the right is basically what it is, because y has both negative and positive values, so you get that parabola. Now over here I've shown you that if you take that parabola and then you rotate it around this vertical line x equal 3, you actually get sort of it kind of looks like maybe a Christmas ornament. So let's just say it's a Christmas ornament. So we want to find the volume of that particular Christmas ornament. Okay, so what I need here, you see this blue right here? That's actually going to be the radius. So this distance from here to here is actually the radius. So what I need to do, let me just show you. Okay, we know the distance. We know the distance from the y-axis to the curve can be represented by this formula here. So x is actually equal to y squared plus 1. Okay? Now, but the distance, if we want the distance between the curve and x equal 3, we actually have to subtract that from 3. So if we subtract that from 3, let me put this up here because it probably makes more sense if I put it up there, if I can get it to cooperate. Okay, so actually it's not lined up properly, but you can still see. So this distance here, if I actually took 3, which would be the distance all the way from here to here, that would be 3. And then if I subtract this distance right here from it, then that would give me the distance between the figure and this vertical line, and that's my radius. So basically I have to take 3 minus the quantity y squared plus 1, and that's my radius. And you can see that over here, so there's my radius. Okay, now I can simplify that because 3 minus 1 is 2, so that's really just 2 minus y squared. Okay, now to actually find since you're actually going to have to integrate this from down here to up here. So to find these y values, you actually need to plug the x value in to the function and then solve it. So if you plug the 3 in here and then solve it, you'll get y squared equals 2. So y would equal plus or minus the square root of 2. So that's why I've got the minus square root of 2 would be here, and the plus square root of 2 would be here. So you're going to have, remember, you're going to have all of these circular cross sections, but you're going to integrate them from y equal minus square root of 2 to y equal plus square root of 2. So that's going to be the limits of my integration. And then we do pi times the radius squared. So 2 minus y squared was the radius, so then we square it. And then you go ahead and square that, and then I'll leave you to integrate it. So if you integrate this from minus square root of 2 to square root of 2, and then of course multiply by pi at the end, you'll actually get 64 square root of 2 over 15 times pi. Now the reason I wanted to show you that is because I want to talk about the washer method. And the washer method says if we generate a solid of revolution and it does not border its axis, then we create washers. See, this example up here, this figure actually borders the actual axis. But if it doesn't border the axis, then there's going to actually be a hole in between it. So consider this example that I just showed you, the one above, and instead of revolving around x equal 3, what if we revolved around the y-axis? Okay, So if we go back up here, so instead of revolving this picture around this line, what if I took this graph right here, and what if I revolved it around the y-axis here? Well, then there would be a hole in here, you know, there would be a hole in here, in other words, a circular hole in between. And so we would get solids here on the outside, but we would have kind of a hole in the middle here. Okay? So we would actually have a hole in the solid. Now, but each horizontal cross section would be the shape of a washer. See, look, when I say washer, I'm talking about basically a kind of like a coin with a hole in the middle, if you will. So, and that washer has an inner radius, say from here to, from here to here, that would be the inner radius, and then it has an outer radius, which would be from here all the way over to here. So I didn't do that real good, but let me use a straight line. So it would have an inner radius, which would be from here to there, and then an outer radius, which would go from there to there. Okay? And so it turns out that the area of that washer, actually there's a formula that we can use for the area of a washer here, and let me highlight it for you. So the area of the washer is actually the area of the large circle minus the small circle. So basically, if you took the area of the large circle, that's the capital R, so that's the big radius, so you would have pi big R squared minus pi little r squared. So the area of the little circle subtracted from the area of the big circle, and then that would give you the area of our washer. Okay, now I wrote this as a function of y, and I'll show you why here, because if you look at your typical washer, okay, so I tried to draw you a diagram here. So the distance from the center of this washer all the way out to here is represented by this blue line, and so that's the large radius, and that radius is 3. So that radius stays the same all the way up and down here. So that stays the same all the way up and down, all the way from minus square root of 2 all the way to square root of 2. That radius will stay the same. But the radius, the inner radius, actually follows the curve. So the inner radius follows the curve. And so that radius would simply be the yellow bar here, or the yellow line here. And it goes from, this is the x value, but remember this function is what? This function is x equal y squared plus 1. So that inner radius would be r equals y squared plus 1. And so your formula then for the area of the washer would be pi times the large radius squared minus pi times the smaller radius squared, and then that would give you the area of a typical washer. And so what you're going to do is the capital R quantity squared, that's this part, and then the little r quantity squared, that's this part here. And so if you put that in the formula, then you'll get a integral that you can evaluate to get that volume. So basically, remember, what we're getting is the volume, just so you understand what we're getting. We're actually getting the volume that's created by this weird looking thing that we end up with when we rotate it around that axis. So it'll be a solid, but it'll have a hole in the middle. The largest hole will be at the top, and then the smallest hole will be in the middle, and then you'll have larger holes down here at the bottom. Okay, so basically we would integrate this from here, which is minus square root of 2, up to here, which is positive square root of 2. So that's your limits of integration. And then I went ahead and pulled the pi out here, so you can factor the pi out of both of these. So I just pulled the pi out here. And then in here I just went ahead and left the difference of these squares. So you have 3 squared minus the quantity y squared plus 1 squared. And then if you evaluate that integral that will actually give you the volume of that solid that's generated. So if you want the washer method about a vertical axis like I did here, then the volume is going to be pi, and then you're going to integrate from the lower level to the upper level, and then you're going to take the outer radius squared minus the inner radius squared dy, and these are going to be functions of y. But if you actually do the washer method where you're revolving something about a horizontal axis, then your A is going to be your leftmost endpoint and your B is going to be your rightmost endpoint, and then your radii are going to be functions of x. So you'll have a function of x squared that'll represent your larger radius, and then you'll have another function of x that represents your smaller radius. Now when I say functions of x, of course they can be constants, because we had a constant up here for the larger radius. So these functions can obviously be constants as well. Okay, so let's look at this example. Let's say we take the region y equal x squared plus 1 and the line y equal minus x plus 3. So in other words, the region bounded by those two graphs, and revolve it about the x-axis. Okay, so here let me show you what this picture is. Okay, so here's the line y equals minus x plus 3, and then here's the graph of y equal x squared plus 1. Now to find where these two intersect, I just set them equal, and you can see I did that down here. So I set the two graphs equal, then solve for x. So I know that this point right here is x equal -2, and this point right here is x equal 1. So that tells me I'm going to actually integrate the washers from -2 over to +1. So you can see here -2 to 1. Okay, now let's talk about the outer radius and the inner radius. So if you'll notice, from the center to the outer radius, that would just be the distance from the x-axis to the blue line, and that's the line y equals minus x plus 3, or just 3 minus x. And then the inner radius would be the distance from here to here, but I went ahead and just showed it down here as the same radius. So it's the distance from here to here. So it's the distance from the x-axis to the parabola, which is just going to be x squared plus 1. So now the volume would be pi integrated from -2 to 1, the outer radius squared, which is 3 minus x, minus the inner radius squared, which is x squared plus 1, quantity squared. And now just freeze the video and then walk through the algebra here, because this is just algebra, and then evaluate the integral, and evaluate the integral, then evaluate the integral from x goes from -2 to +1, and go ahead and calculate the answer. And I got that the answer is 117/5 pi. Okay, one more. The region bounded by y equal x cubed, the line y equal 4x, is revolved about the y-axis. So here's the line y equal 4x. Here's the graph of y equal x cubed. Now notice I wrote these in terms of x though. So this is x equal y over 4. This is x equal the cube root of y. Now the outer radius is just x equal y to the 1/3. The inner radius is the distance from here to here, which would just be x equal y over 4. And so we're going to integrate from 0 to 8, and I'll tell you why in a minute, but pi times integral 0 to 8, take the outer radius and square it, minus the inner radius and square it, and then do all of the work here to get your answer. Okay. Now there's a practice problem down here that you can freeze the video and look at. Okay, but let me go ahead and tell you why I know I'm going from 0 to 8. I know I'm going to integrate these washers from 0 all the way up to wherever this point is. So what I have to do is just find out, just have to set these two graphs equal to one another and then find out where they intersect, and you'll find out that they intersect at y equals 0 and y equal 8. So that's why we go from 0 to 8. That's all I have time on this one, so we'll go to the next section on the next video.